Hello, welcome to MAT 123. This is problem solving in mathematics, and it's intended mostly for elementary teachers or candidates or prospective teachers planning to teach elementary mathematics. So today we're going to talk about lesson 1, which is about the numeration system. And if you're using the MyLab textbook, this is chapter 3.1. Take note that in your MyLab, there are chapter reviews or chapter summaries that are available for you to access. And there are also review examples for homeworks when you start working on your MyLab assignments. So the instruction indicates that the questions below will be assigned or reviewed in class. So pay attention to the instructions given. You may be asked to submit solutions for grading on Blackboard. So once again, pay close attention to the instructions given on the video. You may be asked to submit solutions for grading on Blackboard. Okay, so I want you to take a look on the chart on the screen and think about what you notice and what you wonder about the chart. What do the chart present? What do the chart indicate? You could pause the video and think about your noticings and wonderings. By the way, as this is our first video recording, every time I mention pause the video and do some thinking or reflection, it is advisable that you follow so, because if this is a synchronous class, this is what we will be doing. I'll be asking you a question. I'll give you a few wait time to think about it, and then we share and brainstorm about it. Okay, let's see what you were thinking about. Yeah, I think some people would notice that during the ancient times, the Babylonian times, people used tally marks to record numbers. So they're just using the same character, like a triangle, to represent how many. That is correct. So there's actually also, there are no symbols for zero during the Babylonian and Egyptian times. And also, I think that's also true during the Greek and Roman time. No symbol for zero. So it shows that if nothing is written, that means there's nothing. There's nothing being tallied. So there's no symbol, but indicates nothing, right? Okay, and then eventually during the Hindu and Hindu-Arabic era, there is already a symbol for zero, and that's the zero we use nowadays. Because nowadays we use the Hindu-Arabic system for numbers. What else do you notice? You probably notice that there's a progression from the ancient times to the present. And the reason is to efficiently represent any number. The word efficient signifies that nowadays we have better methods for representing numbers, for counting objects. But during those times, they use tally marks, which means that if you have 1 million objects that you are accounting for, then you have to use 1 million triangles to represent it, and that's a lot. That is very tedious. So it's important that nowadays we are using a very efficient system that is based on place value or position. Back then, the number system only includes the additive property, meaning you just keep adding symbols, keep adding, and it's not so efficient. So what do you wonder? You probably wonder why in the Hindu Arabic system, there are 10 digits. So question, why are there 10 digits? Why not 11? Why not 12? What do you think? So I did a little bit of research on the history of number system, and a lot of the materials that I read presume that this is motivated by the fact that we have 10 fingers. So it's presumed that because we have 10 fingers, and that's why there are 10 symbols. Because human beings naturally count using their fingers. The word digit actually rooted from the word finger in different language. In the Hindu Arabic and Roman period, oh, not including the Roman, it's just the Hindu Arabic and Hindu Arabic, they use the concept of multiplication and division to represent numbers. Whereas here, they use the additive or subtractive property to indicate symbols. Now, I'm going to share with you on Blackboard the doc version of this document, so you could watch the video down here. By clicking the link, you should be able to watch the origin of the word numerate. The word numerate comes from count. So numbers are used to count, okay? But this video gives you more details about this historical development. So let's go to page 2. So what are the definitions of numerals and numeration system? Well, numerals are the symbols that we use to represent cardinal numbers. The word cardinal means principal numbers. And in math, when you say cardinal numbers, you mean counting numbers, numbers that you use to count. Because the numbers that we use to count are the principal numbers, the numbers that we often use in real life. So what is a numeration system? So it's a collection of properties and symbols agreed upon to represent numbers in a systematic way. There is a system, there's like a rule. For instance, in our number 123, we know that the position of tens is 10 times the position of ones. The position of hundreds is 10 times the position of tens. So the system applies such a rule when you introduce an additional symbol. During the ancient times, they used the tally numeration system. So they use single strokes or tally marks to represent each object that is counted. And like I mentioned earlier, these are not so efficient because if you have a million objects that you are representing, then that means you have to write millions of this single stroke, and that's a lot. Okay, so now in the Roman numeral system, as we could see from the chart earlier, there was already development, but the development is not enough to be so efficient, and we'll talk about it now. In Roman numeral, we use I to represent 1, V to represent 5, X to represent 10, L to represent 50, C to represent 100, D to represent 500, and M to represent 1000. So what rule is used in placing a value before a larger value? Notice that in the second table, there is subtraction being applied. And let's see why. So if I want to represent 3, I'm only in Roman numeral. In Roman numeral, 3 is considered to be 3 strokes, right? 3 strokes. And that 3 is represented by the 3 eyes. However, you're not allowed to use more than 3 of the same symbols. So like consecutively, you cannot use 4 i's consecutively. So how does 4 get represented? So we will now use the subtraction property, which means that if you place a unit of that object in front of a bigger value, then you're subtracting 1. So the rule is if you're placing a unit of something before a larger value, then you're subtracting 1. But the larger value should be one of this, right? It cannot be an invented value. Like you cannot put an I before 3 i's to take away, because that doesn't make sense. So you need to use the value, the symbols here in the chart to be able to apply this subtraction property. For instance, if I want to represent 10, all I need to do is use X. But what if I want 9, right? So that means I have to put a 1 in front of the X, because that means subtracting 1 from 10. Now, to represent 50, 50 is 5 tenths, right? So since L is 50, if I want to represent 40, then I'll be using one set of that unit, which is tens, which is X, and take it away from 50. So take note of this conversions here. So I would like to invite you to try writing each of the following numbers, 1, 2, and 3, in Roman number. You can pause the video and then I'll let you check your answers. Okay, so let's begin. 18. 18 is 10 plus 8. So 10 is X, and 8 is 5 plus 3. So that's 18. So how about 449? Since the closest value to 400 is 500, so we need to introduce D to represent 400. So that means we have a D, take away a 100. That's a 400. And then we will use a 40, which means it's an L, 50, take away 10. And then a 9 will be an X, take away 1. I shouldn't put that little symbol there because that's something different. Okay. So this is the symbol for 449. How about 9,999? By the way, did you notice that there is no symbol higher than M? And that's because, which I base on a research, right? So if you put a line on a bar on top of these symbols, it means you're multiplying the number by 1,000. So for instance, X is 10, but if I put a bar, so that's 10 times 1,000, which is the symbol for 10,000. If I put a V with a bar, that means what? So it means 5 times 1,000, which is a 5,000. And if I use an I, no, we don't use an I because there's already a symbol for 1,000, which is M. So we only represent anything beyond M using that bar. So what does a C with a bar represent? What do you think? So a C with a bar will be 100 times 1,000, which is 100,000. So the question is, how do you represent 9,999? Since 10,000 is symbolized by X bar, and we need 9,000, so we could use the subtractive property. So if I put an M in front of that, 10,000 minus 1,000 is 9,000. How about the 900? So that's an M, which is 1,000, take away 100, which is C. How about a 90? So that's going to be a C, take away a 10, which is a 90. That's 100, take away the 10. And then a 9 will be an X, take away a 1. So this is the symbol for 9,999. In MyLab, we will only represent using Roman numbers, numbers that are below 1,000. Okay, so let's continue with Hindu Arabic number system. In the Hindu Arabic number system, all numerals are constructed from 10 digits. We're using 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. There's only 10 symbols that we use. There's 10 numerals. And like I said, this is because presumably we have 10 fingers, and that's why they use 10 symbols. Place value is based on powers of 10, the number base of the system. So 10 is the base of the system. So for instance, if I'm going to write 1, 2, 3, 4 using expanded notation, it means that I have one group of 10 to the third plus two groups of 10 to the second. 10 to the second is 100. So this is thousands. This is hundreds. This is tens, and this is ones. So plus I have three groups of 10 to the first power and 4 times 10 to the 0 power, which is 1. So 10 to the 0, don't forget 10 to the 0 is 1. So 4 times 10 to the power zeros is the same as 4 ones. Now, if you're teaching elementary students and you want the students to conceptually understand how base 10 numbers are represented, we could use what we call the base 10 blocks. So the unit of measure is this little cube. This little cube is called 1 unit, one object, 1 unit of that measurement. And once you already have 10, that 10 will form a new object called a long, because you're only allowed groups of 10s. You cannot go beyond 10. You don't have symbols more than 10. So once a set of units reach 10, it forms a new object called, in this case, we call it a long. A long is one group of 10s. Now, if you have 10 longs, then that forms a new symbol called a flat. 10 longs, which is equal to 100 units, is one flat. What if you have 10 flats? 10 flats will now form a block. It's a group of 10 flats. It's like a cube, right? So how many units are there in a block? So there are 1,000 units in a block because it's 10 groups of hundreds. So this is 10 groups of hundreds. This is 10 groups of tens. This is 10 group of ones. This is 1, okay? All right, so let's go to the next. Okay, so if I have the number 5,678, it means that I have 5,000s or 5 groups of 10 to the third. I have 600s, which is 6 groups of 10 squared, 7 tens, which is 7 groups of 10 to the 1, and 8 units, which is 8 ones. So if I'm going to describe using models, then this is what models you should have to represent this number. So this is 5 blocks plus 6 flats plus 7 longs and plus 8 units. Notice that the symbols are 5, 6, 7, and 8, because we are only allowed to use those 10 digits. In expanded form, 6,789 is 6 groups of thousands, which is 10 to the third. Remember, 10 to the third is 10 times 10 times 10, which is 1,000. 7 groups of 10 squared, which is 7 groups of hundreds. That's 10 times 10, which is 100. We have 8 groups of tens and 9 group of ones, which is also 10 to the 0. So you could write it just as ones or unit, or you could also write it as 10 to the 0. So now let's do some practice on how to write an expanded notation to a regular base 10 numeral. So let's begin. We have the highest power is 10 to the 5th. So that means there's a place value for 10 to the 4th, 10 to the 3rd, 4, 3, 2, 1, and 10 to the 0, which is 1. So the strategy on how to write a numeral in base 10 from an expanded notation is prepare all place values, including and after the highest exponent. So here the highest exponent of 10 is 10 to the 5th. So that means there should be a spot for any other exponent lower than 5. So here we have 4 groups of 10 to the 5th. And we have 6 groups of 10 squared. And we have 7 groups of ones, but we don't have anything else. So that means we have 0 of this, 0 of this, 0 of that. So therefore the base 10 numeral is 400,607. Why don't you try the next one? Pause the video. Okay, so what's the highest power here? So the highest power here is 10 to the 10th. So now we have 10 to the 9, 10 to the 8, 10 to the 7, 10 to the 6, 10 to the 5, 10 to the 4, 10 to the 3, 10 to the 2, 10 to the 1, 10 to the 0. Remember, you're ending up with the units, the 10 to the 0. So we have 8 here. We have 7 here. We have 5 here. And we have 2 here. So that means all the others are zeros. So therefore, our base 10 numeral will be 8000700520. So now we need to put commas to indicate the chunks of place values. So how do you read this number? So this is 80 billion 7 billion 5020. 80 billion. This is billion. This is million. This is thousand. And this is ones. Okay, so 80 billion, 7 million, 5,020. Okay, so let's try these exercises. Base 10 system versus other numeric systems. Consider the number 46583512109. How could you describe the difference between the two fives listed in this number? What do you think? I'll give you a chance to think about it. Okay, so the first 5 is in the place of a million. So this represents 5 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 to the 0, 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 10 to the 8, not 10 to the 9, because this one is 10 to the 0. So you always start counting from 10 to the 0. So this is 5 times 10 to the 8, whereas the other one is, this other 5 is 10 to the 0, 1, 2, 3, 4, 5. 5 times 10 to the 5. So the difference between the two is that the first 5 on the left is, okay, so it's 10 to the third times the 5 on the right. The 5 on the left is 10 to the third times as big as the 5 on the right. How I know it's 10 to the third times? Because the difference between 8 and 5 is 3. Okay, so let's go to the next question. Write the number 4658351 as word, then in expanded notation. How could we represent this number with a visual aid? What about with scientific notation? So let's start with the first part. It says in word. So this is ones, thousands, millions. This is billion. So that's 46 billion. 46 billion. How about the next chunk? That's 583 million. 512,109. You see, it's normal to be tempted to write symbols because words is a lot tedious, okay? So let's see what's the next question is asking. How could we represent this number with a visual aid? With a visual aid. So far we haven't introduced the objects, the blocks that represent numbers more than thousands. Right now, we do not have any symbols available to represent them. So it might be very difficult for us to represent this unless we have a name for billions, millions, and 10,000s, 100,000s, and so on. If the number has only 4 digits, then it's easy for us to represent it using models. We'll do a research. Maybe they have discovered new blocks names to represent numbers higher than, thousands in the place value. What about scientific notation? So how do you write this number in scientific notation? Again, we use scientific notation when we deal with extremely large numbers like this, but it's not practical to use scientific notation because there are not so many significant zeros to the right. We usually just use scientific notation when we have something like 46 billion, right? If we have 46 billion, then the scientific notation for this will be 4.6 times. Let's count the number of place values from the decimal point to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the scientific notation for 46 billion is 4.6 times 10 to the 10. But if we want to really write this in scientific notation, then this is 4.6583512,109 times 10 to the, let's see, I think it's the same number, right? It's 10 to the 10. So that is the scientific notation for that. So for scientific notation, the standard a number is in scientific notation if it can be written as A, where times 10 to the power B, where A is a number between 1 and 10, but it cannot be 10. Notice that I did not use the equal sign here. So you could use anything from 1.0 to 9.9999 and so on. But you cannot use any number higher than 10 or equal to 10. And then B must be an integer, meaning it could be a negative integer, a 0, or a positive integer, but it cannot be a fraction or decimal. So that's how you write a number in scientific notation. So the strategy is to place the decimal point between the first non-zero digit and the digit next to it, and then count how many spaces you move to the right or left to form the original number. And that's the exponent of 10 that you will need. That's the value of B. Okay, let's go to number 3. Give the place value of the underlined digit. Let's start off with letter A. So that's correct. That's a tens. This one, ones, tens, hundreds, thousands, 10,000s. That's the place value of that. Indicate which digit in this number has place value of hundreds. What do you think? Correct, that's a 5. How about 10,000s? That's a 3. How about 10 millions? None. We don't have any digit in the 10 millions. So the answer is none. Do you know that there are bases other than 10? We have base 2, base 3, any number you could think of, etc. There's base 12, etc. Now, what is the principle behind other bases? So if base 10 uses expanded notations that are powers of 10, base 2 uses expanded notations using powers of 2. Makes sense, right? Base 12 uses powers of 12. So think about it as, instead of using groups of tens for blocks or models that represent these numbers, we use a different base. For example, what does 2, 3, 4, base 5 represent? So it means that you have 4 groups of 5 to the 0, 3 groups of 5 to the 1, and 2 groups of 5 to the 2. So let's see what this looks like in regular base 10. What is 2 groups of 5 squared? So 5 squared is 25, so that's 2 times 25, which is 50. 3 groups of 5 to the first, so that's 3 times 5, that's 15. 4 groups of 5 to the 0 or 1 is 4. If we combine this is 69. So this is 69 base 10, the regular base that we use. How about if I have a number in base 2? 1, 0, 1, 1, 1, 0, 1. Okay, base 2. Let's see what this looks like. So this is 1 times 10, 2 to the 0 plus 0 times 2 to the 1 plus 1 times 2 to the 2 plus 1 times 2 to the 3 plus 1 times 2 to the 4 plus 0 times 2 to the 5 and 1 times 2 to the 6. So what is that equal to? What is 2 to the 6? So 2 to the 6 is 64. So the value of this one is 64. Since this is 0 of that, that's a 0. One group of 2 to the 4th. 2 to the 4th is 16. So one group of 16. This is one group of 8. This is one group of 4. No group of 2. And one group of 1, which is 1. So this number, when simplified, will be equal to 64 plus 16 plus 8 plus 4 plus 1, which you can use your calculator. That's going to be 93. It's equivalent to 93. 64 plus 16 is 80. 8 plus 4 is 12 plus 1 is 13. So that's a 93 in base 10. So how do you write the following in base 10 numeral? You could pause the video and try answering the question. Okay, so here are the answers to these 3 questions. I have shown you the work. The strategy is just always consider the base and the powers of the base. So you start from 0 to 1 to 2 and so on. So it's important that you mark the exponents this way. This is 0, 1, 2. These are the exponents of the base, right? And so on. And then that's how you write it in expanded notation. So let's see how many of you got 100 on these 3 questions. So these other pieces will be just left to you as an exercise. We don't need to do this now. I want you to reflect on these questions, and we can probably discuss them during our tutoring session. And remember, in your syllabus, you have your tutoring session schedules. Be careful how you calendar all your schedules. Make sure you have them available to alert you so that you don't miss these tutoring sessions. You are all welcome to attend tutoring sessions and ask questions. So try answering all these problems and be ready to ask during the tutoring session. So, okay, so let's try one challenge before we close this session. What is the fewest number of pieces you can receive in a fair exchange for 11 flats, 17 longs, and 16 units? So the question is asking for the fewest number of pieces. So take note that flats are groups of units. Like a flat is 10 units, right? So since you have 11 flats and you're not allowed to use more than 10 or more of this, then you could trade 10 flats for one, what do you call that? That 100 unit thing. So, oh, this is a flat. So this is a flat, right? I have a long is like this. So let's go back to the problem. So you could trade 10 flats for one block. And so you have one block and one flat left. You could trade 10 longs to one flat, and you have 7 longs left. You could trade 10 units to one long, and you have 6 units left. Let's see, what does that look like? So you have 6 units. One long will be added to 7 longs, so that will be 8 longs. One flat will be added to one flat, so you have 2 flats, and you have a total of 1 block. So from having 11 plus 17 plus 16 different objects, so now you only have 8 plus 6, which is 14, plus 2, which is 16, plus 1, 17 objects or 17 pieces of objects that you receive. And so therefore the numeral for this would be 1, 2, 8, 6. 1, 2, 8, 6. So the way it works, as I could see it, is that you have 16, 17, and 11. So this one goes down, this you add, this you have 2, and then you have 1. So it's 1, 2, 8, 6. And the reason why I wrote it that way is because 17 longs is 17 groups of tens. So that's 170. And 11 flats is 11 groups of hundreds. So that's 1100. So therefore, the shortcut for figuring out is to just use our usual way of converting these symbols into powers of 10. 11 flats is 11 hundreds, 17 longs is 17 tenths, 16 units is 16 ones. So therefore, you could just directly add them vertically to easily get that fewest number of pieces. But I showed you technically, conceptually, how to do it using models. Remember, you're not allowed to use 10 or more of the same object. Okay? If you have any question, please be ready to share these questions during our tutoring sessions. I will leave to you the last problem as an exercise and be ready to respond to it and share your answers during our tutoring hours. So after this, you could replay the video, play it again if you need more, and then you could start working on MyLab lesson number 1, homework number 1. Those are easier than you thought. So, okay, enjoy watching and see you soon. Bye-bye.